Metals and nonmetals. Physical properties. Metals. The easiest way to start grouping substances is by comparing their physical properties. Let us study this with the help of the following activities. Activity. Take samples of iron, copper, aluminum and magnesium. Clean the surface of each sample by rubbing them with sandpaper. Metals in their pure state have a shining surface. This property is called metallic luster. Activity. Take small pieces of iron, copper, aluminum and magnesium. Cut these metals with a sharp knife. These cannot be cut. Hold a piece of sodium metal with a pair of tongs. Always handle sodium metal with care. Dry it by pressing between the folds of a filter paper. Put it on a watch glass and it can be easily cut with a knife because sodium is a soft metal. You will find that metals are generally hard. The hardness varies from metal to metal. Activity. Take pieces of iron, zinc, lead and copper. Place any one metal on a block of iron and strike it 4 or 5 times with a hammer. Some metals can be beaten into thin sheets. This property is called malleability. Gold and silver are the most malleable metals. Activity. Consider some metals such as iron, copper, aluminum, lead, etc. Aluminum metals are also available in the form of wires. The ability of metals to be drawn into thin wires is called ductility. Gold is the most ductile metal. You will be surprised to know that a wire of about 2 km length can be drawn from 1 gram of gold. It is because of their malleability and ductility that metals can be given different shapes according to our needs. Activity. Take an aluminum or copper wire. Clamp this wire on a stand. Fix a pin to the free end of the wire using wax. Heat the wire with a spirit lamp, candle or a burner near the place where it is clamped. After a while, the metal wire heats up and the pin falls down. Metals are good conductors of heat and have high melting points. The best conductors of heat are silver and copper. Lead and mercury are comparatively poor conductors of heat. Activity. Set up an electric circuit. Place the metal to be tested in the circuit between terminals A and B. Connecting a metal wire between A and B can make the current flow easily and the bulb will light up. You must have seen that the wires that carry current in your homes have a coating of polyvinyl chloride, PVC, or a rubber-like material. Something like rubber is an electrical insulator, so that it prevents the current of the wire from being wasted and we can easily catch the wire even though the current is passing. Nonmetals. There are very few nonmetals as compared to metals. Some of the examples of nonmetals are carbon, sulfur, iodine, oxygen, hydrogen, etc. The nonmetals are either solids or gases except bromine, which is a liquid. Do nonmetals also have physical properties similar to that of metals? Let us find out. Activity. Collect samples of carbon, coal or graphite, sulfur and iodine. Nonmetals are also in solid, liquid and gaseous form. Your observations regarding metals and nonmetals. We cannot group elements according to their physical properties alone, as there are many exceptions. For example, first, all metals except mercury exist as solids at room temperature. You have observed that metals have high melting points, but gallium and caesium have very low melting points. These two metals will melt if you keep them on your palm. Second, iodine is a non-metal, but it is lustrous. Third, Carbon is a nonmetal that can exist in different forms. Each form is called an allotrope. Diamond, an allotrope of carbon, is the hardest natural substance known and has a very high melting and boiling point. Graphite, another allotrope of carbon, is a conductor of electricity. Fourth, alkali metals, lithium, sodium, potassium, are so soft that they can be cut with a knife. They have low densities and low melting points. Elements can be more clearly classified as metals and nonmetals on the basis of their chemical properties. Activity. Take a magnesium ribbon and some sulfur powder. Burn the magnesium ribbon. Collect the ashes formed and dissolve them in water. The resultant solution make red litmus paper to blue. The product formed on burning magnesium is basic. Now burn sulfur powder. Place a test tube over the burning sulfur to collect the fumes produced. Add some water to the above test tube and shake. This solution make blue litmus paper to red. The product formed on burning sulfur is acidic. Equations for these reactions. 2 Mg plus O2 gives 2 MgO. MgO plus H2O gives MgOH2. S plus O2 gives O2. SO2 plus H2O gives H2SO3. Most nonmetals produce acidic oxides when dissolved in water. On the other hand, most metals give rise to basic oxides. Chemical properties of metals. Collect the samples of following metals: aluminum, copper, iron, lead, magnesium, zinc and sodium. What happens when metals are burnt in air? Magnesium burns in air with a dazzling white flame. Do all metals react in the same manner? Let us check by performing the following activity. Activity. Caution. It would be better if students wear eye protection. Aluminum, copper, iron, lead, magnesium, zinc and sodium. Hold any of the samples taken with a pair of tongs and try burning over a flame. Repeat with the other metal samples. Collect the product if formed. Let the products and the metal surface cool down. Magnesium metals burn easily. When the metal is burnt, the color of flame: aluminum, white flame; copper, a greenish blue flame; magnesium, a blazing white flame; and sodium, yellow flame. The metal surface after burning appears shiny. Arrange the metals in the decreasing order of their reactivity towards oxygen. Na greater than Mg, greater than Al, greater than Zn, greater than Fe, greater than Pb, greater than Cu. Aluminum, copper, iron, zinc are processed with oxygen. The resulting product is insoluble in water. Magnesium and sodium are processed with oxygen. The resulting product is soluble in water. Almost all metals combine with oxygen to form metal oxides. Metal plus oxygen gives metal oxide. For example, when copper is heated in air, it combines with oxygen to form copper oxide, a black oxide. 2Cu plus O2 gives 2CuO. Similarly, aluminum forms aluminum oxide. 4Al plus 3O2 gives 2Al2O3. Metal oxides are basic in nature, but some metal oxides such as aluminum oxide, zinc oxide, etc. show both acidic as well as basic behavior. Such metal oxides which react with both acids as well as bases to produce salts and water are known as amphoteric oxides. Aluminum oxide reacts in the following manner with acids and bases. Al2O3 plus 6HCl gives 2AlCl3 plus 3H2O. Al2O3 plus 2NaOH gives 2NaAlO2. sodium aluminate plus H2O. Most metal oxides are insoluble in water and some of these dissolve in water to form alkalis. Sodium oxide and potassium oxide dissolve in water to produce alkalis as follows. Na2 plus H2O gives 2NaOH. K2O plus H2O gives 2KOH. All metals do not react with oxygen at the same rate. Different metals show different reactivities towards oxygen. Metals such as potassium and sodium react so vigorously that they catch fire if kept in the open. Hence, to protect them and to prevent accidental fires, they are kept immersed in kerosene oil. At ordinary temperature, the surfaces of metals such as magnesium, aluminum, zinc, lead, etc. are covered with a thin layer oxide. The protective oxide layer prevents the metal from further oxidation. Iron does not burn on heating, but iron fillings burn vigorously when sprinkled in the flame of the burner. Copper does not burn, but the hot metal is coated with a black-colored layer of copper oxide. Silver and gold do not react with oxygen even at high temperatures. You must have observed that sodium is the most reactive of the samples of metals taken here. The reaction of magnesium is less vigorous, implying that it is not as reactive as sodium. But burning in oxygen does not help us to decide about the reactivity of zinc, iron, copper or lead. Let us see some more reactions to arrive at a conclusion about the order of reactivity of these metals. What happens when metals react with water? Activity. Collect the samples of following metals: aluminum, copper, iron, lead, magnesium, zinc and sodium, calcium, gold, silver, potassium. Put small pieces of the samples separately in beakers half filled with cold water. Sodium, calcium, potassium metals react with cold water. The increasing order of their reactivity with cold water is Ca smaller than Na smaller than K. Metals like potassium and sodium react violently with cold water. In case of sodium and potassium, the reaction is so violent and exothermic that the evolved hydrogen immediately catches fire. 2K plus 2H2O gives 2KOH plus H2 plus heat energy. 2Na plus 2H2O gives 2NaOH plus H2 plus heat energy. Potassium and sodium metal produce fire on water. Calcium and magnesium metal start floating after some time. The reaction of calcium with water is less violent. The heat evolved is not sufficient for the hydrogen to catch fire. Ca plus 2H2O gives CaOH2 plus H2. Calcium starts floating because the bubbles of hydrogen gas formed stick to the surface of the metal. Magnesium does not react with cold water. It reacts with hot water to form magnesium hydroxide and hydrogen. It also starts floating due to the bubbles of hydrogen gas sticking to its surface. Metals like aluminum, iron and zinc do not react either with cold or hot water, but they react with steam to form the metal oxide and hydrogen. 2Al plus 3H2O gives Al2O3 plus 3H2. 3Fe plus 4H2O gives Fe3O4 plus 4H2. Metals such as lead, copper, silver and gold do not react with water at all. Arrange the metals in the decreasing order of reactivity with water. K greater than Na, greater than Ca, greater than Mg, greater than Al, greater than Fe. Metals react with water and produce a metal oxide and hydrogen gas. Metal oxides that are soluble in water dissolve in it to further form metal hydroxide. But all metals do not react with water. Metal plus water gives metal oxide plus hydrogen. Metal oxide plus water gives metal hydroxide. What happens when metals react with acids? Metals react with acids to give a salt and hydrogen gas. Metal plus dilute acid gives salt plus hydrogen. But do all metals react in the same manner? Let us find out. Activity. Collect the aluminum, copper, iron, magnesium and zinc metal samples. If the samples are tarnished, rub them clean with a sandpaper. Put the samples separately in test tubes containing dilute hydrochloric acid. Suspend thermometers in the test tubes so that their bulbs are dipped in the acid. Observe the rate of formation of bubbles carefully. Magnesium metals react vigorously with dilute hydrochloric acid. With magnesium metal, record the highest temperature. The metals in the decreasing order of reactivity with dilute acids. Mg greater than Al, greater than Zn, greater than Fe, greater than Cu. Equations for the reactions of magnesium, aluminum, zinc and iron with dilute hydrochloric acid. Mg plus H2SO4 gives MgSO4 plus H2. 2Al plus 3H2SO4 gives Al2SO4 3 plus 3H2. Zn plus H2SO4 gives ZnSO4 plus H2. Fe plus H2SO4 gives FeSO4 plus H2. Hydrogen gas is not evolved when a metal reacts with nitric acid. It is because HNO3 is a strong oxidizing agent. It oxidizes the H2 produced to water and itself gets reduced to any of the nitrogen oxides N2O, NO, NO2. But magnesium and manganese react with very dilute HNO3 to evolve H2 gas. You must have observed that the rate of formation of bubbles was the fastest in the case of magnesium. The reaction was also the most exothermic in this case. The reactivity decreases in the order Mg greater than Al, greater than Zn, greater than Fe. In the case of copper, no bubbles were seen and the temperature also remained unchanged. This shows that copper does not react with dilute HCl. How do metals react with solutions of other metal salts? Activity. Take a clean wire of copper and an iron nail. Put the copper wire in a solution of iron sulfate and the iron nail in a solution of copper sulfate taken in test tubes. Record your observations after 20 minutes. The iron nail in a solution of copper sulfate test tube. Find that a reaction has occurred. Fe plus CuSO4 gives FeSO4 plus Cu. During the process, the color of solution changes from blue to green, which indicates that the process has taken place. This is displacement reaction. Reactive metals can displace less reactive metals from their compounds in solution or molten form. We have seen in the previous sections that all metals are not equally reactive. Displacement reactions give better evidence about the reactivity of metals. It is simple and easy. If metal A displaces metal B from its solution, it is more reactive than B. Metal A plus salt solution of B gives salt solution of A plus metal B. Iron metal is more reactive than copper metal based on observation. The reactivity series. A series of different metals being arranged in decreasing order of their reactivity are called reactivity or activity series. Activity series. Relative reactivities of metals. K potassium, Na sodium, Ca calcium, Mg magnesium, Al aluminum. These metals are more reactive. Zn zinc, Fe iron, Pb lead, H hydrogen, Cu copper, Hg mercury, Ag silver. These metals reactivity is decreases. Au gold metal, this metal is least reactive. How do metals and nonmetals react? Noble gases, which have a completely filled valence shell, show little chemical activity. We, therefore, explain the reactivity of elements as a tendency to attain a completely filled valence shell. Let us have a look at the electronic configuration of noble gases and some metals and nonmetals. Electronic configuration of some elements. We can see from table that a sodium atom has one electron in its outermost shell. If it loses the electron from its M shell, then its L shell now becomes the outermost shell, and that has a stable octet. The nucleus of this atom still has 11 protons, but the number of electrons has become 10. So there is a net positive charge giving us a sodium cation Na+. On the other hand, chlorine has 7 electrons in its outermost shell and it requires one more electron to complete its octet. If sodium and chlorine were to react, the electron lost by sodium could be taken up by chlorine. After gaining an electron, the chlorine atom gets a unit negative charge because its nucleus has 17 protons and there are 18 electrons in its K, L and M shells. This gives us a chloride anion Cl-. So both these elements can have a give and take relation between them. Sodium and chloride ions, being oppositely charged, attract each other and are held by strong electrostatic forces of attraction to exist as sodium chloride NaCl. It should be noted that sodium chloride does not exist as molecules but aggregates of oppositely charged ions. Let us see the formation of one more ionic compound, magnesium chloride. The compounds formed in this manner by the transfer of electrons from a metal to a non-metal are known as ionic compounds or electrovalent compounds. Name the cation Mg+ and anion Cl- present in MgCl2. Properties of ionic compounds. To learn about the properties of ionic compounds, let us perform the following activity. Activity. Take samples of sodium chloride, potassium iodide, barium chloride or any other salt from the science laboratory. The physical state of these salts is solid. Take a small amount of a sample on a metal spatula and heat directly on the flame. Repeat with other samples. Flame color after heat. Sodium chloride, yellow. Potassium iodide, light purple. Barium chloride, from pink to white. Try to dissolve the samples in water, petrol and kerosene. Sodium chloride, soluble in water, insoluble in petrol, insoluble in kerosene. Barium chloride, soluble in water, insoluble in petrol, insoluble in kerosene. Potassium iodide, soluble in water, insoluble in petrol, insoluble in kerosene. Make a circuit and insert the electrodes into a solution of one salt. Aqueous solution of sodium chloride, barium chloride and potassium iodide conducts electricity. Sodium chloride, barium chloride and potassium iodide nature is ionic. Melting and boiling points of some ionic compounds. Ionic compounds. NaCl. Melting point 1074 Kelvin. Boiling point 1686 Kelvin. Ionic compounds LiCl. Melting point 887 Kelvin. Boiling point 1600 Kelvin. Ionic compounds CaCl2. Melting point 1045 Kelvin. Boiling point 1900 Kelvin. Ionic compounds CaO. Melting point 2850 Kelvin. Boiling point 3120 Kelvin. Ionic compounds MgCl2. Melting point 981 Kelvin. Boiling point 1685 Kelvin. You may have observed the following general properties for ionic compounds. First, physical nature. Ionic compounds are solids and are somewhat hard because of the strong force of attraction between the positive and negative ions. These compounds are generally brittle and break into pieces when pressure is applied. Second, melting and boiling points. Ionic compounds have high melting and boiling points. This is because a considerable amount of energy is required to break the strong interionic attraction. Third, solubility. Electrovalent compounds are generally soluble in water and insoluble in solvents such as kerosene, petrol, etc. Fourth, conduction of electricity. The conduction of electricity through a solution involves the movement of charged particles. A solution of an ionic compound in water contains ions, which move to the opposite electrodes when electricity is passed through the solution. Ionic compounds in the solid state do not conduct electricity because movement of ions in the solid is not possible due to their rigid structure. But ionic compounds conduct electricity in the molten state. This is possible in the molten state since the electrostatic forces of attraction between the oppositely charged ions are overcome due to the heat. Thus, the ions move freely and conduct electricity. Occurrence of metals. The Earth's crust is the major source of metals. Seawater also contains some soluble salts such as sodium chloride, magnesium chloride, etc. The elements or compounds which occur naturally in the Earth's crust are known as minerals. At some places, minerals contain a very high percentage of a particular metal and the metal can be profitably extracted from it. These minerals are called ores. Extraction of metals. Some metals are found in the Earth's crust in the free state. Some are found in the form of their compounds. The metals at the bottom of the activity series are the least reactive. They are often found in a free state. For example, gold, silver, platinum, and copper are found in the free state. Copper and silver are also found in the combined state as their sulfide or oxide ores. The metals at the top of the activity series is that K, Na, Ca, Mg and Al are so reactive that they are never found in nature as free elements. The metals in the middle of the activity series Zn, Fe, Pb, etc. are moderately reactive. They are found in the Earth's crust mainly as oxides, sulfides or carbonates. You will find that the ores of many metals are oxides. This is because oxygen is a very reactive element and is very abundant on the Earth. Thus, on the basis of reactivity, we can group the metals into the following three categories. First, metals of low reactivity. Second, metals of medium reactivity. Third, metals of high reactivity. Different techniques are to be used for obtaining the metals falling in each category. Several steps are involved in the extraction of pure metal from ores. A summary of these steps. Each step is explained in detail in the following sections. Enrichment of ores. Ores mined from the earth are usually contaminated with large amounts of impurities such as soil, sand, etc. called gangue. The impurities must be removed from the ore prior to the extraction of the metal. The processes used for removing the gangue from the ore are based on the differences between the physical or chemical properties of the gangue and the ore. Different separation techniques are accordingly employed. Extracting metals low in the activity series. Metals low in the activity series are very unreactive. The oxides of these metals can be reduced to metals by heating alone. For example, cinnabar (Hgs) is an ore of mercury. When it is heated in air, it is first converted into mercuric oxide HgO. Mercuric oxide is then reduced to mercury on further heating. 2Hgs plus 3O2. in the presence of heat gives 2HgO plus 2SO2. 2HgO in the presence of heat gives 2Hg plus O2. Similarly, copper, which is found as Cu2S in nature, can be obtained from its ore by just heating in air. 2 Cu2S plus 3O2 in the presence of heat gives 2 Cu2O plus 2SO2. 2 Cu2O plus Cu2S in the presence of heat gives 6 Cu plus SO2. Extracting metals in the middle of the activity series. The metals in the middle of the activity series, such as iron, zinc, lead, copper, etc., are moderately reactive. These are usually present as sulfides or carbonates in nature. It is easier to obtain a metal from its oxide as compared to its sulfides and carbonates. Therefore, prior to reduction, the metal sulfides and carbonates must be converted into metal oxides. The sulfide ores are converted into oxides by heating strongly in the presence of excess air. This process is known as roasting. The carbonate ores are changed into oxides by heating strongly in limited air. This process is known as calcination. The chemical reaction that takes place during roasting and calcination of zinc ores can be shown as follows. Roasting. 2ZnS plus 3O2 in the presence of heat gives 2ZnO plus 2SO2. Calcination. ZnCO3 in the presence of heat gives ZnO plus CO2. The metal oxides are then reduced to the corresponding metals by using suitable reducing agents such as carbon. For example, when zinc oxide is heated with carbon, it is reduced to metallic zinc. ZnO plus C gives Zn plus CO. Obtaining metals from their compounds is also a reduction process. Besides using carbon to reduce metal oxides to metal, sometimes displacement reactions can also be used. The highly reactive metals such as sodium, calcium, aluminum, etc. are used as reducing agents because they can displace metals of lower reactivity from their compounds. For example, when manganese dioxide is heated with aluminum powder, the following reaction takes place. 3MnO2 plus 4Al gives 3Mn plus 2Al2O3 plus heat. These displacement reactions are highly exothermic. The amount of heat evolved is so large that the metals are produced in the molten state. In fact, the reaction of iron oxide Fe2O3 with aluminum is used to join railway tracks or cracked machine parts. This reaction is known as the Thermit reaction. Fe2O3 plus 2Al gives 2Fe plus Al2O3 plus heat. Extracting metals towards the top of the activity series. The metals high up in the reactivity series are very reactive. They cannot be obtained from their compounds by heating with carbon. For example, carbon cannot reduce the oxides of sodium, magnesium, calcium, aluminum, etc. to the respective metals. This is because these metals have more affinity for oxygen than carbon. These metals are obtained by electrolytic reduction. For example, sodium, magnesium and calcium are obtained by the electrolysis of their molten chlorides. The metals are deposited at the cathode is that the negatively charged electrode, whereas chlorine is liberated at the anode, the positively charged electrode. The reactions are: at cathode, Na plus plus E minus gives Na. At anode, 2Cl minus gives Cl2 plus 2E minus. Similarly, aluminum is obtained by the electrolytic reduction of aluminum oxide. Refining of metals. Ores metals produced by various reduction processes described above are not very pure. They contain impurities which must be removed to obtain pure metals. The most widely used method for refining impure metals is electrolytic refining. Electrolytic refining. Many metals such as copper, zinc, tin, nickel, silver, gold, etc. are refined electrolytically. In this process, the impure metal is made the anode and a thin strip of pure metal is made the cathode. A solution of the metal salt is used as an electrolyte. On passing the current through the electrolyte, the pure metal from the anode dissolves into the electrolyte. An equivalent amount of pure metal from the electrolyte is deposited on the cathode. The soluble impurities go into the solution, whereas the insoluble impurities settle down at the bottom of the anode and are known as anode mud. Corrosion. Iron, when exposed to moist air for a long time, acquires a coating of a brown flaky substance called rust. Let us find out the conditions under which iron rusts. Take 3 test tubes and place clean iron nails in each of them. Label these test tubes A, B and C. Pour some water in test tube A and cork it. Pure boiled distilled water in test tube B. Add about 1 ml of oil and cork it. The oil will float on water and prevent the air from dissolving in the water. Put some anhydrous calcium chloride in test tube C and cork it. Anhydrous calcium chloride will absorb the moisture, if any, from the air. Leave these test tubes for a few days and then observe. You will observe that iron nails rust in test tube A, but they do not rust in test tubes B and C. In the test tube A, the nails are exposed to both air and water. In the test tube B, the nails are exposed to only water, and the nails in test tube C are exposed to dry air. Iron corrodes when it comes in contact with water and air. Prevention of corrosion. The rusting of iron can be prevented by painting, oiling, greasing, galvanizing, chrome plating, anodizing, or making alloys. Galvanization is a method of protecting steel and iron from rusting by coating them with a thin layer of zinc. The galvanized article is protected against rusting even if the zinc coating is broken. Alloying is a very good method for improving the properties of a metal. We can get the desired properties by this method. For example, iron is the most widely used metal, but it is never used in its pure state. This is because pure iron is very soft and stretches easily when hot. But if it is mixed with a small amount of carbon, about 0.05%, it becomes hard and strong. When iron is mixed with nickel and chromium, we get stainless steel, which is hard and does not rust. Thus, if iron is mixed with some other substance, its properties change. In fact, the properties of any metal can be changed if it is mixed with some other substance. The substance added may be a metal or a non-metal. An alloy is a homogeneous mixture of 2 or more metals or a metal and a non-metal. It is prepared by first melting the primary metal and then dissolving the other elements in it in definite proportions. It is then cooled to room temperature. If one of the metals is mercury, then the alloy is known as amalgam. The electrical conductivity and melting point of an alloy is less than that of pure metals. For example, brass, an alloy of copper and zinc. Cu and Zn, and bronze, an alloy of copper and tin, Cu and Sn, are not good conductors of electricity, whereas copper is used for making electrical circuits. Solder, an alloy of lead and tin, Pb and Sn, has a low melting point and is used for welding electrical wires together.